Economic optimization. Effective managerial decision-making is the process of efficiently arriving at the best possible solution to a given problem. When alternative courses of action are available, the best decision is the one that produces a result most consistent with managerial objectives. The process of arriving at the best managerial decision is the process of economic optimization. Expressing economic relations. Economic relationships can be expressed in the form of equations, tables, or graphs. When the relationship is complex, however, expressing the relationship in equational form is crucial. For example, suppose that the relationship between the total revenue, TR, of a firm and the quantity, Q, of the good or service that the firm sells over a given period of time, say 1 year, is given by TR equals 100Q minus 10Q squared. By substituting various hypothetical data for the quantity sold, we generate the TR schedule of the firm, shown in figure 2.1. Plotting TR schedule, we get the TR curve. Note that the TR curve rises up to Q equals 5 and declines thereafter. Thus, we see that the relationship between the total revenue of the firm and its sales volume can be expressed in equational, tabular, or graphical form. Marginals as the derivatives of functions. A marginal value is a change in a dependent variable associated with a one-unit change in an independent variable. Consider the general function y equals f of x. Using delta to denote change, it is possible to express the change in the value of the independent variable x by the notation delta x and the change in the dependent variable y by delta y. Thus, a general specification of the marginal concept is delta y over delta x. The change in y, delta y, divided by the change in x, delta x, indicates the change in the dependent variable associated with a one-unit change in the value of x. The concept of the derivative is closely related to the marginal concept. A derivative is a precise specification of the marginal relation. More generally, the derivative of y with respect to x is given by the change in y with respect to x as the change in x approaches 0. By convention, economists use d to represent very small changes in a variable. Hence, dy over dx means changes in y relative to very small changes in x. For changes between two distinct points, the delta sign is used. For example, for change in x between 2 and 4 in figure 2.1, the average dy over dx is 40. For smaller change in x between 2 and 3, the average dy over dx is 50. Note that the smaller the change in x, the closer is the value of the derivative to the slope of the curve at a point. Rules of differentiation. The rules of differential calculus is a simple method to compute marginal values. 1. Constant function rule. The derivative of a constant function, y equals f of x equals a, is 0 for all values of a, the constant. For example, for the function y equals 3, dy over dx is equal to 0. Since y is defined to be a constant, its value does not change for any value of x, and so dy dx, the slope of the line is 0 as in figure below. Number 2, power function rule. The derivative of a power function y equals ax raised to b, where a and b are constants, is equal to the exponent b multiplied by the coefficient a times the variable x raised to the b minus 1 power. For example, given the function y equals 3x, where a equals 3 and b equals 1, that is, dy dx is equal to 3. This is graphed below. Note that the slope of the line dy dx is constant at the value of 3 over any range of x values. Another example, for the function y equals x cubed, that is, its derivative is dy dx equals 3x squared. Note that the slope of the curve dy dx varies at every value of x. This is graphed below. Number 3, sums and differences rule. The derivative of a sum difference is equal to the sum difference of the derivatives of the individual terms. Thus, if u equals g of x and b equals h of x, where u is an unspecified function g of x, while b is another unspecified function h of x, then for the function y equals u plus minus b, dy dx equals du dx plus minus dv dx. For example, if u equals g of x equals 3x and b equals h of x equals x cubed, so that y equals u plus v equals 3x plus x cubed, dy dx equals 3 plus 3x squared. Since du over dx is equal to 3 and dv over dx equals 3x squared by the power function rule, the derivative of the total function dy dx is equal to the derivative of the sum of its parts, 3 plus 3x squared. As another example, for y equals 0.01x cubed minus 0.1x squared plus 10x plus 8, dy over dx is equal to 0.03x squared minus 0.2x plus 10. Note that the derivatives of the first three terms of the y functions are obtained by the power function rule, while the derivative of the constant 8 is equal to 0 by the constant function rule. Number 4, product rule. The derivative of a product of two expressions is equal to the first expression multiplied by the derivative of the second, plus the second expression times the derivative of the first. Thus, for the function y equals u times v, where u equals g of x and v equals h of x. For example, for the function y equals 5x squared times quantity 8 minus 3x, and letting u equals 5x squared and v equals 8 minus 3x. The derivative of the function therefore is dy over dx equals 80x minus 45x squared. Number 5, quotient rule. Given the function y equals u over v, its derivative can be expressed as dy over dx equals to v times du over dx minus u times dv over dx all over v squared. For example, suppose we have the following function, y equals 5x minus 9 over 10x squared. Using the formula and letting u equals 5x minus 9 and v equals 10x squared, we obtain the following. dy over dx is equal to 18 minus 5x all over 10x cubed. Function of a function rule or the chain rule. If y equals f of u, where u equals g of x, then dy over dx equals dy over du times du over dx. For example, if y equals 2u minus u squared and u equals 2x cubed, then dy over dx is found as follows. dy over du equals 2 minus 2u. Substituting for u creates the expression dy over du equals 2 minus 2 times 2x cubed equals 2 minus 4x cubed. du over dx equals 6x squared. dy over dx is equal to dy over du times du over dx equals 12x squared minus 24x to the fifth. Let me mention to you again the 6 rules of differentiation which can be used to calculate marginal values. 1. We have the constant function rule. 2. We have the power function rule. 3. The sums and differences rule. 4. Product rule. 5. Quotient rule. And 6. Function of a function or chain rule. Determining maximum or minimum value. To distinguish between a maximum and a minimum point, we use the second derivative. For the general function y equals f of x, the second derivative is written as d squared y over dx squared. For example, y equals x cubed. Its first derivative is equal to 3x squared, and its second derivative is equal to 6x. The rule is if the second derivative is positive, we have a minimum, and if the second derivative is negative, we have a maximum. Geometrically, the derivative refers to the slope of the function, while the second derivative refers to the change in the slope of the function. The second derivative is used to distinguish between points of maximization and minimization. It is always negative when evaluated at a point of maximization and positive at a point of minimization. Illustration 2.1. Given the following TR function, TR equals 45Q minus 0.5Q squared. Its first derivative, dTR over dQ, equals 45 minus Q. Setting the first derivative equal to 0, we have 45 minus Q equals 0. Therefore, Q is equal to 45. Since the second derivative is equal to negative 1, this TR function reaches a maximum at Q equals 45. Another example is provided by profit maximization by U Incorporated. Suppose that the TR and TC functions of U Incorporated are TR equals 45Q minus 0.5Q square, TC equals Q cubed minus 8Q square plus 57Q plus 2. Now, to calculate the profit function, we simply get the difference between the TR and TC function. And the profit function, therefore, is equal to negative Q cubed plus 7.5Q squared minus 12Q minus 2. Now, to determine the level of output at which the firm maximizes profits, we proceed as follows. So, we simply derive the first derivative of the profit function. d pi over dq equals negative 3q squared plus 15q minus 12, equated to 0. And by simply using the technique of factoring, we have quantity minus 3q plus 3 and quantity q minus 4, equating it to 0. Now, we can easily calculate the values of q, which is q equals to 1 and q equals to 4. Now, which of these values of q that will maximize our profit? So, we simply make use of the second derivative. Therefore, q equals to 1 and q equals to 4. Pero saan ba sa mga values na ito ang magbibigay ng maximum profit para sa U Incorporated? We simply evaluate using the second derivative of the profit function, which is equal to negative 6q plus 15. Now, we evaluate at q equals to 1. So, we have negative 6 times 1 plus 15 equals 9. So, this is positive. Therefore, profit is minimum. How about at q equals to 4? So, we have negative 6 times 4 plus 15, which is equal to negative 9. So, profit is maximum. Therefore, profit is maximized at q equals 4. And from the original profit function, we can determine that the profit where q equals to 4 is 6. Marginal analysis in decision making. Why is marginal analysis important? Economists reason that the optimal decision is to continue any activity up to the point where the marginal revenue or benefit equals the marginal cost. That is, MR equals MC. In business situations, firms often have to make careful calculations to determine, for example, whether the additional revenue received from increasing production is greater or less than the additional cost of the production. Marginal analysis allows the manager to identify an optimal decision, that is, the course of action that will maximize management objective. Marginal analysis can be defined as the amount of change in a dependent variable that results from a unit change in an independent variable. This change is represented by the slope of the line if the functional relationship is linear. Illustration 2.2. Consider the following profit function. Pi equals negative 10,000 plus 400q minus 2q squared, where pi, this is the total profit, and q, this is output in units. As shown in figure 2.2, if output is 0, the firm incurs a 10,000 pesos loss. But as output rises, profit also rises. Break-even points are output levels where profit is 0 and are reached at 29 and 171 units of output. Profit rises as output expands to 100 units of output where profit is maximized at 10,000 pesos and declines thereafter. The profit maximizing output is calculated by finding the derivative of the function, then determining the value of Q at which the derivative or marginal is equal to 0. So you have here the marginal profit equals to the first derivative of the profit function, which is equal to 400 minus 4Q. So equating it to 0, we have 400 minus 4Q equals 0. And then solving it simultaneously, we calculate that the Q is equal to 100 units. Therefore, when Q is equal to 100, marginal profit is 0 and total profit is at a maximum. Beyond Q equals 100, marginal profit is negative and total profit is decreasing. Additional illustration. The key to identifying Happy Mushrooms Incorporated exact output daily harvest level at which maximum profit is attained is to compute the marginal profit at any given level of output. Maximum profit occurs at an output where marginal profit is 0. That is, the slope of the tangent line is 0. Figure 2.3 shows an enlarged profit graph with tangent lines drawn at daily harvest of 3.1, 3.3, and 3.4 kilograms. Thus, we draw some simple conclusions. 1. At 3.1 kilograms, the tangent is upward sloping. Marginal profit is positive, that is, raising output by a small amount increases total profit. Second conclusion from figure 2.3. At 3.4 kilograms, the tangent is downward sloping. Marginal profit is negative. So, a small reduction in output would increase total profit. Third conclusion. At 3.3 kilograms, the tangent is horizontal. That is, the tangent slope and marginal profit are 0. Maximum profit is attained precisely at this level of output. Calculating marginal profit at any level of output by the simple rules of differential calculus given Happy Mushrooms profit equation. That is, profit function is equal to negative 100 plus 132Q minus 20Q squared. Taking the first derivative of this profit function, we have the marginal profit, d pi over dq, equals to 132 minus 40q. Now, equating this to 0, we have 132 minus 40q equals 0. By simple calculation, our q therefore is equal to 3.3 kilograms per day. Therefore, at 3.3 kilograms daily harvest, Happy Mushrooms' marginal profit is 0. This is the output that maximizes profit. But at what price is required for Happy Mushroom to sell this quantity? The answer is found by substituting Q equals to 3.3 kilograms into its price equation, given by P equals to 170 minus 20Q. And then we simply substitute our Q equals to 3.3. So P is equals to 104 pesos. It is interesting to reiterate that at the optimum output Q equals 3.3 kilograms, total profit reaches a peak while marginal profit is exactly equal to 0. Now, let's have multivariate optimization. So far, we've discussed a lot about economic optimization. Now, what is multivariate optimization? It's the process of optimization for equations with three or more variables. For example, demand is often a function of the product's price, advertising, income, and other factors. Similarly, cost is determined by output, input prices, technology, etc. As a result, multivariate optimization is often employed in the process of optimization. Now, when analyzing multivariate relations, one is interested in the marginal effect of each independent variable on the dependent variable. Optimization requires an analysis of how a change in each independent variable affects the dependent variable, holding constant the effect of all other independent variables. The partial derivative is the concept used for this type of marginal analysis. As an illustration, consider Happy Toad's company demand function. Q equals 8,000 minus 10p plus 40a plus pa minus 0.8a squared minus 0.5p squared, where Q is the quantity, P the price in pesos, A advertising expenditure in hundreds of pesos. To maximize the value of this function, each partial must equal to 0. So we have the partial derivative of the demand function with respect to P is equal to negative 10 plus A minus P equals 0. Now, the partial derivative of Q with respect to A is equal to 40 plus P minus 1.6 A equal to 0. Solving these two equations simultaneously yields A equals to 50 and P equals to 40. Therefore, the maximum value of Q is equal to 8,800 units. Constrained optimization. Most of the time, firms face constraints in their optimization decisions. For instance, limitations on production capacity, availability of skilled personnel, or supply of crucial raw materials. It may also face legal and environmental constraints. In such cases, we have a constrained optimization problem, such that the maximizing or minimizing of an objective function subject to some constraints. Constrained optimization problems can best be solved expediently by differential calculus. Frequently, decision variables can be changed only within certain constraints. Here's an example about supply commitment. The CEO of a firm is trying to determine the company's profit maximizing output level. By contract, it already is committed to supplying at least 7 units to its client. Suppose its estimated profit function is pi equals 40q minus 4q squared. The CEO seeks to maximize profit subject to Q greater than or equal to 7 units. Traditionally, we set marginal profit equal to 0. So we have the first derivative of the profit function with respect to Q is equal to 40 minus 8Q equal to 0, so that Q equals to 5. This value is infeasible. That is, it violates the contract constraint. The constrained maximum occurs at Q equals 7, where the first derivative of the profit function with respect to Q, or the marginal profit, is equal to negative 16. Note that since the marginal profit is negative, profit would decline if Q were increased. The CEO would like to raise profits by decreasing Q, but this is impossible due to the binding contract. To use the method of Lagrange multiplier, we create a new variable z for the constraint q equals 7 and write the Lagrangian function, which is equal to 40q minus 4q squared plus z times quantity 7 minus q. In short, we have formed L, denoted the Lagrangian, by taking the original objective function and adding to it the binding constraint multiplied by z variable. Solve the partial derivative with respect to the two variables q and z and set them equal to 0. That is, the partial derivative of the Lagrangian function with respect to q is equal to 40 minus 8q minus z equals 0. Now, the partial derivative of the Lagrangian function with respect to z is equal to 7 minus q equals 0. Next step. Solving this equation simultaneously yields z equals negative 16 and q equals 7. We find that q equals 7 and z equals negative 16. The value of q is the best the CEO can do. The z value measures the marginal profit at the constrained optimum. Example 2 for constrained optimization. Multiple markets. A company has a limited output and must decide what quantities Q1 and Q2 to sell to different market segments. Suppose it seeks to maximize total profit given by the following profit function, which is equal to quantity 20 Q1 minus 0.5 Q12 plus 40 Q2 minus Q2 squared, subject to Q1 plus Q2 less than or equal to 25. Setting the marginal profit equal to 0 for each quantity, so we have the derivative of the profit function with respect to Q1 equals 20 minus Q1 equals 0, and the derivative of the profit function with respect to Q2 equals 40 minus 2 Q2 equals 0. We find that Q1 equals 20 and Q2 equals 20. But these desired quantities again are infeasible. The total 40 equals Q1 plus Q2 exceeds the available supply, which is 25. To continue solving this problem, at the optimal solution, marginal profit must be equal. Thus, the partial derivative of the profit function with respect to Q1 is equal to the partial derivative of the profit function with respect to Q2 must hold, as well as Q1 plus Q2 equals 25. Now, taking the derivatives, we have 20 minus Q1 equals 40 minus Q2. Solving this equation and the quantity constraint simultaneously, we have Q1 equals 10 and Q2 equals 15. Thus, Q1 equals 10 and Q2 equals 15 is the company's optimal solution. We validate our solution by applying the method of Lagrange multiplier. We write the Lagrangian function as follows: equals to 20 Q1 minus 0.5 Q1 squared plus 40 q2 minus q2 squared plus z times the constraint 25 minus q1 minus q2, where the binding constraint is q1 plus q2 equals 25. And z again denotes the Lagrangian multiplier. Setting the appropriate partial derivatives equal to 0, we find the partial derivative of the Lagrangian function with respect to q1 equals 20 minus q1 minus z equals 0. The partial derivative of the Lagrangian function with respect to q2 equals 40 minus 2 q2 minus z equals 0. And the partial derivative of the Lagrangian function with respect to z equals 25 minus q1 minus q2 equals 0. Notice that the third condition is simply the original constraint. Finding the values that satisfy these three equations simultaneously, we calculate q1, q2, and z variable. Now, we have values that satisfy the three equations simultaneously. That is, q1 equals 10, q2 equals 15, and z equals 10. The values for q1 and q2 confirm the original solution. In addition, note that z equals 20 minus q1 is also equal to 40 minus 2 q2, or z is the marginal profit for q1 and the marginal profit for q2. In other words, the multiplier z represents the common value of the marginal profit. The actual value of the marginal profit in each market is z equals 10. Thus, ang ibig sabihin nato, if the company could increase total sales above 25, it would increase profit by 10 pesos per unit of additional capacity. Example number 3, cost minimization. Organic corporation wants to minimize the following TC function, which is equal to 4q1 squared plus 5q2 squared minus q1 q2, subject to the constraint that q1 plus q2 equals 30. Restate the constraint so that an expression is formed that is equal to 0. So we have 30 minus q1 minus q2 equals 0. Then, if we multiply it by an unknown variable z and add the result to the TC function we want to minimize, we get the Lagrangian function, which is equals to 4q1 squared plus 5q2 squared minus q1 q2 plus z times 30 minus q1 minus q2. To solve the constraint optimization problem, all we need to do is optimize the Lagrangian function. For example, in the case of organic corporation, we must find the values of q1, q2, and z that minimize our Lagrangian function. To do this, we must find the partial derivative of the Lagrangian function with respect to each of these three variables, q1, q2, and z. Now, the partial derivative of the Lagrangian function with respect to q1 is equal to 8q1 minus q2 minus z equals 0. The partial derivative of the Lagrangian function with respect to q2 is equal to negative q1 plus 10q2 minus z equals 0. As for the partial derivative of the Lagrangian function with respect to z is equal to negative q1 minus q2 plus 30 equals 0. Solving the systems of equation for q1 and q2, we get the optimal values of q1 and q2. We find that q1 is equal to 16.5 and q2 equals 13.5. Therefore, the optimal value of q2 is 13.5 and q1 is 16.5. Specifically, z measures the change in the variable to be minimized if the constraint is relaxed by 1 unit. If organic corporation wants to minimize TC, subject to the constraint that total output of bulk product is 31 rather than 30, the value of Z indicates by how much the minimum value of TC will increase. What is the value of Z? So the value of Z is simply 118.5. Consequently, if the constraint is relaxed so that total output is 31 rather than 30, the total cost will go up by 118.5 pesos. Yun po ang ibig sabihin ng ating Z variable. For many managerial decisions, information of this sort is of great value. Suppose that a client asks Organic Corporation 115 pesos for one of its products. But to make this product, Organic Corporation would have to stretch its total output to 31 per hour. On the basis of these above calculations, Organic Corporation would be foolish to accept this offer, since this extra product would raise its cost by 118.5 pesos, which is 3.5 pesos more than the amount the client offers to pay for it. In general, a Lagrangian multiplier Z indicates the marginal effect on the objective function of decreasing or increasing the constraint requirement by 1 unit. Now, to summarize our discussion about economic optimization, we have the following points. 1. Economic relationships can be expressed in the form of equations, tables, or graph. 2. The concept of the derivatives is closely related to the marginal concept. 3. The rule is if the second derivative is positive, we have a minimum. And if the second derivative is negative, we have a maximum. Number 4 point from our discussion. Economists reason that the optimal decision is to continue any activity up to the point where marginal revenue or benefit equals the marginal cost. Simply, MR equals MC. And number 5, optimization requires an analysis of how a change in each independent variable affects the dependent variable, holding constant the effect of all other independent variables. So that summarizes our discussion for this lecture related to economic optimization.